Kick tolerance is one of the most critical concepts in drilling engineering, yet it is often misunderstood or oversimplified. In simple terms, kick tolerance is the maximum volume of formation fluid that can enter the wellbore without causing formation fracture or loss of well control when the kick is circulated out. Understanding kick tolerance is essential because it directly determines whether a well can be drilled safely without exceeding fracture pressure at the weakest point in the wellbore, which is conventionally the casing show. To understand kick tolerance, we first need to understand what happens during a kick. A kick occurs when formation pressure exceeds the hydrostatic pressure of the drilling fluid, allowing formation fluids such as gas, oil, or water to flow into the wellbore. When this influx happens, the well is shut in and the kick is circulated out using controlled procedures. However, as the kick is circulated to surface, the annular pressure increases, and this additional pressure is applied to the formation, especially at the casing show or weakest exposed formation. If this pressure exceeds the fracture pressure, losses can occur, potentially leading to a drop in the hydrostatic level and eventually an uncontrolled blowout. This is where kick tolerance becomes crucial. Kick tolerance defines how much influx the well can tolerate without causing formation breakdown during circulation of the influx out of the well. If kick tolerance is low, even a small influx can be dangerous. If it is high, the well has a greater margin of safety. Therefore, kick tolerance is not just a theoretical concept, it directly influences casing design, mud weight selection, and overall well planning. Kick tolerance is primarily controlled by four key factors: formation fracture gradient, pore pressure, casing show depth, and mud weight. The fracture gradient determines how much pressure the formation can withstand before breaking. The pore pressure represents the pressure of fluids within the formation. The casing show depth defines the weakest exposed point in the well, and the mud weight determines the baseline hydrostatic pressure in the wellbore. Any change in one of these factors will directly affect kick tolerance. One of the most important locations when evaluating kick tolerance is the casing show. The casing show is usually the weakest point because below it the formation is exposed and unprotected by casing. As we go deeper, formations tend to be more compacted due to higher overburden pressure, hence tend to be stronger. During kick circulation, if the pressure at the show exceeds the fracture pressure, losses occur, reducing hydrostatic pressure and potentially leading to an uncontrolled situation. That is why kick tolerance calculations almost always focus on pressure at the casing show. Gas kicks are especially dangerous when it comes to kick tolerance. Gas expands significantly as it rises, which increases annular pressure due to reducing effective hydrostatic pressure. This expansion can rapidly push pressures beyond the fracture limit, even if the initial influx volume was small. For this reason, kick tolerance is usually calculated assuming a gas kick, making it a conservative and safer design approach. Kick tolerance calculations are typically done during the well planning phase. Engineers calculate the maximum allowable kick volume that can be safely circulated out without exceeding fracture pressure at the casing show. If the calculated kick tolerance is too small, adjustments must be made. These adjustments may include setting casing deeper, increasing mud weight, or redesigning the well trajectory. In many cases, kick tolerance directly determines where casing strengths are set. During drilling operations, kick tolerance also plays a role in decision-making. For example, if a well is being drilled with a narrow pressure window, the kick tolerance may be very limited. This means the crew must be extremely vigilant in detecting early signs of kicks, such as bed volume gain, flow rates increase, or changes in pump pressure. Early detection reduces the influx volume and keeps the kick within tolerable limits. Another important aspect of kick tolerance is its relationship with equivalent circulating density, or ECD. When circulating drilling fluid, annular pressure losses increase the effective density of the mud. If ECD becomes too high, it can approach or exceed fracture pressure even without a kick. When a kick is present, the combined effect of ECD and shut-in pressures can significantly reduce kick tolerance. This is especially critical in deep water, extended reach, and HPHT wells. Kick tolerance is also closely linked to well control procedures. Methods such as the driller's method and the weight-and-weight method both aim to circulate the kick out while maintaining bottom hole pressure constant. However, regardless of the method used, the maximum pressure applied during circulation must stay within the limits defined by kick tolerance. Exceeding these limits can lead to lost circulation, underground blowouts, or complete loss of well control. In modern drilling operations, software tools are often used to model kick tolerance more accurately. These tools simulate gas migration, pressure behavior, and temperature effects to provide a more realistic picture of well response during a kick. However, even with advanced software, the basic principles remain the same. Keep pressures below fracture limits and maintain sufficient hydrostatic control. A common misconception is that increasing mud weight always improves kick tolerance, while higher mud weight increases hydrostatic pressure and reduces the likelihood of a kick. It also increases ECD and may reduce the margin to fracture pressure. In some cases, increasing mud weight can actually reduce kick tolerance rather than improve it. This is why kick tolerance must always be evaluated as part of a balanced pressure management strategy. Kick tolerance is especially critical in wells with narrow drilling windows, such as HPHT wells, depleted reservoirs, and deep water environments. In these cases, the difference between pore pressure and fracture pressure may be very small, leaving little room for error. Even a small influx can exceed tolerable limits, making accurate calculations, real-time monitoring, and disciplined operational practices essential. In conclusion, kick tolerance is a fundamental concept that lies at the heart of safe drilling operations. It defines how much formation influx a well can safely handle and directly influences casing design, mud programs, and well control strategies. Ignoring or underestimating kick tolerance can lead to catastrophic consequences, while proper understanding and application significantly reduce the risk of well control incidents. For drilling engineers, supervisors, and rig crews, mastering kick tolerance is not optional, it is a critical requirement for drilling safe and successful wells.